Hi, I'm Pulkit Tandon. I'm a graduate student at Stanford University. And today I'll be talking about our work on CAMB, which is Contrast Aware Multi-Scale Banding Index. This is joint work with Mariana, Joel, and Lucas from Netflix. CAMB is an objective metric to determine the presence of banding. So what is banding artifact? So in this slide template, what you see on the left is basically an example of banding artifact. So banding artifacts are basically artificial staircase-like contours, which are introduced during the quantization of a smoothly spatially varying signal. They are visible in large smooth regions with small gradients. So these regions might be like sky, ocean, dark scenes, etc. So as you can see here, you see like these artificial steps. So these are basically the banding artifacts. So now let's look at a more realistic example. So this is an example of a sunrise scene. And depending on your display right now, you may or may not be able to see banding artifacts which are present in the sky. So here in this scene, there is an intensity ramp going from the sun to the periphery, which is being quantized, resulting into a staircase-like contours which are present in this region. No worries if in your display, if you couldn't see it. Here is a toy example with fake colors to highlight the bands. Here, a random color was used to highlight an intensity level. And you can see that there is a kind of bands which are occurring in this whole periphery region. And these basically manifest themselves as staircase-like contours, which can be seen in this original plot. Okay, so now that we know what are banding artifacts, why do we care about them? So these banding artifacts are present even in content from top streaming services and can be viewed on even HD screens when you are viewing high bit depth or high resolution content. Traditional video quality metrics such as PSNR, SSIM, VMAP are not designed for banding detection, and they can't detect the incidence of banding in inputs. Finally, it is even a problem for latest codecs like VP9 and EV1. So in that sense, banding detection is a really timely problem to attack. So, okay, I've talked about banding detection, but what are we even detecting in this case? So like I talked about, banding artifacts are basically artificial staircase-like contours, which are occurring due to quantization, right? So this essentially is a contrast detection problem, though not any contrast, but rather these artificially introduced steps. And hence, like if we want to detect banding, we need to figure out we basically need to figure out the visibility of these contrasts. And then what affects the banding visibility? So banding visibility can be largely determined by contrast sensitivity function, which basically depends on the perceived contrast across a step and the spatial frequency of steps. And on the right, here is a typical example from a human visual study, which shows this contrast sensitivity function. On the y-axis, you have the contrast. On the x-axis, you have the spatial frequency. And you can see like as your spatial frequency or contrast increases, initially your visibility to this contrast detection increases and eventually it falls down like a typical hump-shaped function. So if we want to build a good banding detector, we need to be able to tackle both this contrast sensitivity and spatial frequency visibility issues. And this is exactly what CAMB does. So CAMB, or Contrast Aware Multi-Scale Banding Index, basically tackles both this issue by first being contrast aware, which accounts for the contrast sensitivity axis of this curve. And it also has a multi-scale component, which accounts for the spatial frequency. Okay, so let's summarize what CAMB does. So CAMB is a no reference distortion specific metric to banding. It's extremely simple and intuitive with very few hyperparameters and visually motivated computational motifs. Finally, it estimates banding visibility across various encoding parameters like quantization parameters, which are typically used during encoding of a video, but not only that, and also encoding resolution and incidence of differing. So past works have largely focused on banding dependence on quantization parameters, but in this work, we also decided to include encoding resolution and incidence of differing because they clearly directly influence the contrast sensitivity function, where encoding resolution basically affects the spatial frequency and dithering basically affects the perceived contrast. Okay, so now let's look at the block diagram of how CAMB works. So CAMB basically takes input a video and outputs a single number estimating the banding visibility in the video, which is CAMB. It goes through multiple blocks. So first it does some pre-processing on the input video, followed by a multi-scale banding confidence, where actually pixel-wise banding maps are extracted to account for the banding visibility in the frame. And finally, these maps are pooled spatiotemporally. In next few slides, I'll go into the details of these blocks. So first step of CAMB is pre-processing. Here the assumption is that we have encodes of 8-bit, and these encodes are being viewed on a 4K resolution screen. But the encodes can have any resolution and various encoding parameters. So how pre-processing works is that first we extract the Luma component. So we only work with the Luma in this work. We convert the 8-bit to the 10-bit content. We pass it through a low pass filter, which basically acts like an anti-dithering filter. And finally, we upscale the whole thing to 4K. So in these screenshots, you can see like an example of like how this step works. So on the left, I have a original frame, a snippet of an original frame, which is 8-bit dithered and at source resolution. The checkerboard patterns which you see are basically corresponding to the thing. As you can see, they are not across all the edge, but they may or may not occur depending on the encoding parameters chosen. After the pre-processing steps, what we get is a smooth signal at 10-bit. It's undetected, and all the intensity values at this in this frame, in this small snippet, now are in steps of 1, because we do both upsampling and upscaling. And the main reason for doing this pre-processing is that it tackles presence of dithering straight away by doing this anti-dithering step, and it ensures that same routine is followed irrespective of the original encode resolution. Okay. So next step is multi-scale banding confidence, and this is the main workhorse of the CAMB. So this step is largely derived and modified based on this paper by Bhagwati et al. In 2009. What this paper does is that for each pixel, it calculates a banding confidence at a scale S. What the scale means is basically a neighboring window around the pixel. In this work, they explicitly calculate pixels which are within the fraction of ±1 to find out the steps which are occurring in the encode. And these pixels are found in ±1 region in a fashion which avoids texture, which basically is based on a prior that you only consider pixels with gradient less than some hyperparameter to ensure that this belongs to a smoothly varying spatial signal. Okay, so we modified this approach by first making it contrast aware. So now instead of looking at just pixels within ±1, we look at pixels within ±k. And we basically extract pixel-wise banding maps at these different intensities. In our work, we chose like 4 pixel level CAMB maps because we are upscaling our encodes from 8-bit to 10-bit. This is followed by upscaling step. So how we tackle the spatial frequencies by downsampling the original encode by 2 from 4K up to 135p. We don't vary the scale at which these bands are being detected. We keep it fixed, and that's a hyperparameter in our algorithm. So this basically leads to 5 CAMB maps per pixel level map. So per intensity K, you get 5 maps. So in total, you get 20 different CAMB maps. So let's look at how these CAMB maps look like. So I'm going to show you these CAMB maps for the example which I showed you earlier. So the sunrise scene. So here what I am showing is basically these CKS values. So these are 4 different frames, 4 different CAMB maps for the same frame at different values of K. So bands are being detected at different perceived contrast. In this case, we are working with a frame which don't have any dithering, and the warmer colors basically indicate a higher banding confidence. So you can see that here in C4S, you get like lots of these bands which were corresponding to the bands which were present in the original scene here. But you don't get much in the perceived contrast steps which are below than 4. And that's basically happening because we are looking at a frame with explicitly no dithering. And hence, like all these steps in 8-bit are basically converted to 10-bit in steps of 4. But now, if you also have a frame which has dithering, which is like now the lower row, the upper row is same as the previous figure. Now what you see is that instead of C4S, which is like at a perceived contrast step of 4, you basically get a lot more banding confidence detection at a perceived contrast step of 1. And this is basically happening because dithering, when passed through low pass filter, creates values which are at steps less than 4. And hence it tells that, oh, with a frame with dithering, you're basically perceiving less contrast. Okay, how do these maps look spatially, like with the multi-scale step? So now we are going to focus at just one value of K, which is 4. And this is the same frame with no dithering shown up previously. So as you go from the 4K and you downsample it by 2 to 1080p, so on and so forth to 135p, you are basically now detecting bands at lower and lower spatial frequency. So at 4K, you detect like lots of these banding confidence near the sun, where the contours were really tight. Whereas at 135p, you detect bands away from the sun, which are where it had a lower frequency. So in the last step of CAMBI, we basically first spatially pool these CAMBI maps and then also pool them temporarily to get a score for the video. So the spatial pooling largely works on the intuition that like we are basically working in this red box region of the contrast sensitivity function. And hence we can pool proportionally to contrast sensitivity and spatial frequency. Note that spatial frequency here is in log scale. So spatial pooling is essentially just linear combination of these CAMBI maps proportional to contrast and the spatial frequency. We also chose just a worst case. We also pool only worst case banding pixels. And this is to account for the fact that as viewers, we are only typically focused on the worst case banding present in the scene. Finally, temporal pooling is done by first temporarily subsampling the video. In our case, we subsample every half second and then just average the scores. This works well in our case because we are working with single shot scenes mostly, but this can be in future, we'll also try various different temporal pooling methods. Finally, CAMBI has like very few hyperparameters, which are summarized in these tables. So CAMBI just has these 5 hyperparameters. And compared to previous work, which had like typically a large number of hyperparameters, we hope this ensures better generalization of CAMBI to different content. Okay, so now I'm going to talk about how CAMBI was validated. So first, I'm quickly going to talk about the data set which we use for CAMBI validation. So in our data set, we had 9 4K 10-bit sources, which were Netflix video. And one source explicitly was chosen such that it had no banding. These were encoded using AV1 encodes to 8-bit, and these samples were anywhere from 1 to 5 seconds in duration. Our typical generation pipeline was source was first downsampled to a particular resolution and bit depth, and finally encoded using an AV1 encode. The downsampling step could be done using FFmpeg or just direct downsampling. This was done because when you downsample using FFmpeg, it introduced the thing based on the QP or the resolution at which that that video was encoded. So to explicitly account for the case for the thing, when the thing is present in the video, we also had one encode at the highest quality to account for it. Finally, we also did quality control, and we only chose videos which had greater than 80 VMAF and greater than 40 PSNR, highlighting the problem that VMAF and PSNR are not actually able to detect banding at all. Okay, so here in this slide, I summarize the subjective study. So in our subjective study, we had 86 videos, 23 participants, and we work on a DCR scale. In the first plot here on the left, on the y-axis, I have the mean opinion scores. The mean opinion scores went from 100, which is imperceptible, meaning the banding was imperceptible, or perceptible but not annoying, going all the way down to like 0, where banding basically made the video unwatchable or very annoying. And what left plot basically shows, and on the x-axis, I have video index, a random video index. What left plot basically shows is that we had a thorough coverage of the scale. And what right plot here is showing is that we had a confidence interval of our scores below 10. Okay, so to the main result, CAMBI is basically found CAMBI to be linearly correlated with the subjective scores. So here again on the y-axis, I have the mean opinion scores, and on the x-axis, I have first CAMBI, then VMAP, and finally PSNR. And you can clearly see where CAMBI is linearly correlated with mean opinion score, VMAP and PSNR are largely uncorrelated. And here are some numerical results from the paper. For the purpose of this talk, let's just focus on the highlighted components. So for Spearman rank order correlation coefficient, as well as Pearson linear correlation coefficient, we see that VMF and PSNR are basically almost uncorrelated with the mean opinion score, whereas CAMBI had a high correlation number, like 0.92. We also compared it with 2 previous work, B-band and DBI. The open source codes were released after the paper submission, so these results are not in the paper. And we saw that CAMBI performs much better than these 2. Finally, we also show that CAMBI is unbiased over a range of video quality, so it doesn't account for other artifacts. For doing that, we picked up another data set, which is this HEVC data set. And here what we are trying to show is that on the y-axis, we have VMAP, and on the x-axis, we have CAMBI. For HEVC data set, we see VMAP has a range of scores, whereas CAMBI scores are still mostly included within, limited within 5, which basically builds confidence in CAMBI. So in future, we plan to extend CAMBI for 10-bit encodes. We want to verify CAMBI for different encodes. We'll integrate it as a feature in VMAP, and finally, we'll use it for the development of debanding algorithm. In conclusion, I showed you guys that banding is a major problem with current video codecs. Contrast-aware multi-scale banding index, or CAMB, tries to account for detection of these banding artifacts. It's a no reference and distortion specific metric. It's robust to multiple encoding parameters, and it's simple and intuitive. Finally, through our results, we showed that it had high correlation and near linear relationship with mean opinion scores, and it's unbiased over a range of video qualities. Thank you.